Thank you for joining us for the final HPL seminar of the semester. After this, we will have a nice break for the summer and then come back in September for more seminars. So enjoy this one and join us again next term. But for today, we have 3 speakers, so a little bit different from our usual seminars. And we'll have each speaker talk about some part of their expedition to Bolivia. So it's a pretty exciting talk, and they will cover their own parts. So I will start by introducing both of our student speakers today, and then they will go one after the other. So our first speaker of the 2 is Leah Mann. She is currently a PhD student in the Department of Kinesiology. And previously, she's done an undergraduate degree from MRU in health sciences, which she completed in 2018, which following that, she went on to do a master's degree from the University of Waterloo under her current supervisor, Dr. Paolo Dominelli, which she completed in 2021. And her thesis in her master's was focused on principal hypercapnic chemosensitivity. From then, she started a PhD under Dr. Paolo Dominelli, and now she's a 4th-year student here at the University of Calgary, studying the effects of exercise physiology and looking at muscle fatigue and hypoxia. A fun fact about Leah is that she broke her jaw in the middle of her PhD on a teeter-totter. For those of you that know, that word doesn't work very well in this lab here, so maybe steer clear of teeter-totter. Our second speaker of the day is going to be Victoria Chang, who is also a PhD student here in the Faculty of Kinesiology. And previous to being here, she was at the University of Waterloo. She did her BSc in kinesiology there with a minor in medical physiology from 2017 to 2022, which was followed by an MSc degree also in kinesiology with a focus on physiology and nutrition from 2022 to 2024. She then started her PhD here at the University of Calgary under Dr. Paolo Dominelli, and she will be talking about some of her work in her talk today. Fun facts about Victoria are that she competed internationally in paddling and at the varsity level in rowing during her undergrad and master's degrees. And she was also actively involved as a strength and conditioning coach during that time. So I will let the first speaker come and introduce the talk for today, who is their supervisor, Dr. Dominelli, and then he will pass it on to the students. Thank you, all of you.
Great, thank you. So I'm just going to do a little quick introduction to the expedition that we went on, just so students don't have to kind of repeat it a bunch of times. So what did we do? So we went to Bolivia.
You have turned your mic off, so you can turn it back.
There we go. Better?
Yeah.
Okay. So we went to Bolivia in 2024 in July. This is part of a fairly large expedition. So it was led by Trevor Day and Richard Wilson here. So Trevor is actually a professor at Mount Royal University and is a U of C alumni, and Richard Wilson is a faculty member in the Cummings School of Medicine. Fairly large team. You can see there's people from UBC, us, Missouri, lots of other people from Calgary, and then different places internationally. We did it over about 17 days, both here in Calgary. We did some testing at Mount Royal University, and then traveled to La Paz, Bolivia, and many things. Well, we're going to present on today is a very small subset of the entire expedition. It ranged from the effects of high altitude on sleep, the gut microbiota, exercise physiology, anything you can kind of think of. So we're just going to kind of talk about our few projects that we did. That was mostly on exercise physiology. So if you're wondering why Bolivia, so Bolivia is a South American country. Here you can see it's a landlocked country, pointer, next to Brazil and Peru. And we can see here down at the bottom is Bolivia is fairly unique in that there's a part of Bolivia that's very low elevation. You can see that's there in the east. And then there's a part of very high elevation in Bolivia that kind of comes up into the Andes Mountain. And so where we went to was La Paz. So this is an image of La Paz here. So it's at about 3,500 meters elevation. So it's a very significant altitude. Here in Calgary, we're about 1,100 meters. And you actually fly into the city of El Alto, which is just above here at 4,100 meters. So it's a fairly high elevation, not of course as high as you can get in the world, but fairly high for a large city and for a continuous population. So for those who are soccer fans or kind of sports fans, you may have heard of La Paz. in Bolivia specifically, because there's a lot of sports controversy in about the last 10 years. So for a year, FIFA actually banned any kind of competition in La Paz. And they kind of said anything above 2,400 or 2,500 meters, it wasn't allowed to play. And this was in part through some complaints through the Brazilian team. So Neymar had a quote where he said it was inhumane to play in such conditions, field, altitude, ball, everything bad. And there's all them breathing on some compressed oxygen. I think this is in between halves during the game. The ban only lasted a year. They reversed it. There was actually a lot of political firestorms associated with this I won't get into. Bolivia's response is they built a new stadium at El Alto at 4,100 meters. So that's where they now have their World Cup qualifier game. So this is kind of El Alto. It's a big, huge plateau. You can see up there. There's the stadium right there. So needless to say, it's not fun to play at that elevation. So the three studies we're going to talk about, Leah's going to talk about super maximal VO2 max at high altitude. Victoria's going to talk about hypobaric hypoxia and the peripheral chemosensors. The last one's done by my other student, Ben, who's unfortunately can't be here today. So I'm going to talk about the stuff that he investigated. So like to kind of, with any expedition, there's always things that don't go so well. This one was no different. About 5 days before we were supposed to start, there was a coup in Bolivia, in La Paz. And so this actually only lasted for a day, thankfully, but that was a lot of stress for all of us, a lot of calling of NIC equivalents in our own departments of what should we do, what shouldn't we do, turned out to be okay. And this was also a WestJet strike at the same time, so almost everybody who flew in got delayed to some degree coming in. And then there was COVID, because why not? A bunch of people inadvertently COVID and passed it along to other people. So this is just part of the course with expeditionary work. So quick outline of what we did. We spent about 6 days in Calgary to do the baseline testing. Bolivia is not simple to get to, so it takes a few days to get there between all the flights. Up to 3,500 meters is where the institute that we did all the studies were. Here's the team here on a little boat cruise in Bolivia. This is what it looked like down at Mount Royal University. Barbecue after, of course. There's us setting up our lab. We took over one of the anatomy labs during the summer and they weren't using it. And this is what the lab looked like in Bolivia. So you kind of got to make do with where you are. So there's the bike we took down, everything kind of set up on the table, and then there's us testing on the side there. So with that, I'm going to turn it over to Leah.
I like to switch here.
Yeah. Okay, so. Okay.
Use errors.
Hmm?
Use the errors.
Yeah, I know, I'm just. My study was on the supramaximal verification of VO2 at high altitude. So to start with, if we're looking at the oxygen cascade, so this is how oxygen is being moved from the atmosphere into our muscles and tissues. So to start with, if you look at the purple line here, or on this graph, the oxygen partial pressure is on the y-axis. And so you can see that in the atmosphere, there's a nice high partial pressure of oxygen. And as you move through the cascade and oxygen moves through the trachea into your alveoli and into your arterial blood, you're going to see this decrease in partial pressure as you move through this cascade. And you're going to see this nice big drop as the partial pressure of oxygen in the mitochondria is quite low. And so this is acts as the driving force to move oxygen from the atmosphere into our tissues so that we can use it. However, when somebody is in hypoxia, whether that's hypobaric and you're at a high altitude, or normal baric and you're breathing a lower percentage of oxygen, you're going to see a decrease in this partial pressure. And as a result, you're then going to see a decrease in the partial pressure of oxygen available at every part of the cascade, which is going to limit that driving pressure of oxygen into your tissues. And so hypoxia is going to pose a significant limitation on somebody's VO2 max. So when we're looking at VO2 max, there's this whole idea around trying to confirm whether or not somebody has actually achieved a VO2 max. Typically, we would, or ideally, we would look for a plateau in their VO2. And so you would hope to see less than 150 milliliters of change in their VO2 with an increase in work rate. So you might want to see this nice flat line. However, if you don't see that, even though that's our like standard criteria or like gold standard, You would maybe look at some secondary criteria such as heart rate or blood lactate, but these values and criteria are slightly less well defined, which makes it more difficult to first definitely confirm that somebody has reached their VO2 max. So a different method is called supramaximal verification. And so the idea behind this is that after somebody does an incremental maximal exercise test, they'll take a break for a little bit, and then they're going to do this supramaximal exercise bout. So a short bout of high intensity exercise at about 105 or 110% of the maximum work rate that they finish during their incremental test. So the idea being that they do this short bout of high intensity exercise, and their maximum or their oxygen uptake should go back up to whatever their max was, and then you're able to see if that was the same or different than the incremental test that they just finished. So previously, this test has been done at low altitude or in normobaric hypoxia. Our lab actually did a study looking at the normobaric hypoxia. So this graph here, we see the supramaximal duration on the x-axis here, and then on the y-axis, we have their supramaximal VO2 as a percentage of their incremental. So when you see that somebody, as they got to the end of their supramaximal exercise bout, you can see that that VO2 was around 100% of their incremental test. So we showed that these were similar values, and it was an effective use and verification tool at low altitude, but in hypoxia. So then our question for this trip was to confirm if this method of supramaximal verification was effective at confirming VO2 max in hypobaric hypoxia, so at a high altitude. And we hypothesized that the supramaximal verification would be successful. So our actual protocol, we had 20 participants from the people on the trip. There was 10 of them that were female, 10 that were male. And so this is what the protocol looked like. So they would do an incremental maximal exercise test. Females started at 20 watts, while males started at 60 watts. This was the same for both Bolivia and when we were in Calgary. Then participants would cycle for 20 minutes at 20 watts, and then increase by 20 watts every 2 minutes up until they reached volitional fatigue. So then the participants would stop. We would let them hop off the bike and take a little break. They'd rest for about 15 minutes or so. We would get them back on the bike, and then they would do that bout of supramaximal exercise. So we did a work rate of 105% of their final work rate they completed during the max test or the incremental test. We would get them on the bike. We would start them at the same workload, so 20 watts for females and 60 watts for males. We would ramp them up really rapidly over about 15 seconds, just to give them a chance to get their legs moving and get them up to that max work rate. And then they would cycle for as long as they could at that 105%. And this usually lasted anywhere from 1 minute to 3 minutes, kind of depending on the participant. The goal was for them to just go for as long as they could. And so then when we're looking at our analysis of the verification and the incremental test, we're looking at if these values were the same, because we want basically the verification to confirm that they've reached the same VO2 max. So in order to analyze it, we pre-chose the equivalence bounds of this 150 milliliters or 0.15 liters per minute, because that's the gold standard in the plateau, that it's going to change by less than that. So we wanted to see if the supramaximal VO2 was within 150 milliliters per minute of that incremental. And we chose this ahead of time to help prevent any kind of bias when you're looking at the data afterwards. So for our actual results, this table is showing the results from the maximal exercise test, like the incremental one. So we have our low altitude and our high altitude here. We have things like work rate, heart rate, saturation, VO2, and we can see that when they were at high altitude, these values decreased in everybody. And they were significantly lower than when they were at low altitude, but this is what we would expect to see. Then when we look at the actual supramaximal exercise results, the duration for both low altitude and high altitude was around 75 seconds. And then all the rest of these values here, the supramaximal is being expressed as a percentage of the incremental. So if heart rate is 96%, that means the supermax heart rate was 96% of their incremental. But we showed that there was no differences between the percentages that they achieved in both high altitude and low altitude. So even though their actual max heart rate would have been different, they both achieved the same, or people in both locations achieved that same percentage of their max. Except heart rate was a tiny little bit higher, and then ventilation was also reached a slightly higher percentage. But VO2, we achieved the same percentage in both locations. So then when we look at that equivalence testing, so again, we were testing to see if our results were the same, instead of testing to see whether or not they were different or not different. So the equivalence testing, when we had those bounds, we did find that, they were statistically similar at both low altitude and high altitude. So you can see those p-values of 0.07 and 0.001. Showing that we did in fact see the same results. So we showed that that super maximal exercise produced the, verified basically that incremental exercise test. Then when we look at the data, on this graph between the relationship of the two, so incremental is on our x-axis and the super maximal VO2 is on the y-axis. You can see a nice, tight fit to this, regression here, showing that everybody did have a pretty similar, super maximal VO2 as they did in the incremental, which is what our equivalence testing told us. You can also see that, each of these dots is color coded for the same participant in all the graphs. So you can see that most people followed this line really nicely, which is what we hope to see. And then lastly, if we look at these blind Altman plots, look for any kind of like bias in our, super maximal verification. On the y-axis, we have the change from super maximal to incremental VO2. And then the x-axis is that average VO2. And you can see that there's a really nice spread of all the data, between those confidence intervals, not really trending in one direction or another. This was similar to the previous work we had in our lab in the, normal baric hypoxia, where we showed that, below 5 liters a minute of an absolute VO2, we do see a nice spread of the data, which matches what we saw, both in Calgary and in Bolivia, because nobody had a VO2 of above, barely even 4 liters per minute. However, when you get above 5 liters a minute, so people who are as they're getting more fit, you do see some of this negative bias. And you'll see that the super maximal verification is a little less reliable, but, ours, because people were not quite as fit, we did see this nice, reliability of the super maximal verification. So overall, we showed that super maximal verification, was successful in the hypobaric hypoxia, providing us with VO2 values, within, 0.15 liters per minute. So this is confirming that this technique was successful at high altitude in non-acclimated participants, making it an effective tool in the context of hypobaric hypoxia for researchers, at high altitude.
Okay, so for our second study is we're looking at the effects of hyperbaric hypoxia and exercise on peripheral hyperkinetic chemosensitivity. So to begin, peripheral chemoreceptors can be found in our carotid aortic bodies, so near the carotid artery, also the aorta, and they are sensitive to a multitude of stimuli, but primarily they're receptive of changes in partial pressures of arterial O2 and arterial CO2, so PaO2, PaCO2. And what we're looking at is the sensitivity of chemoreceptors, peripheral chemoreceptors, to changes in PaCO2. So an increase in PaCO2 will lead to an increase in methylation, and this is a response that we're studying. So this chemo response can be potentiated by a few things. So with exercise, in a previous study, we have found that peripheral hypercapnic chemosensitivity will increase with exercise from rest. So on this graph on the far left, we have VCO2 on the x-axis and we have chemo response on the y-axis. We see a nice increase from rest to exercise, but as we further increase in intensity, there is no further increase in chemo response. The chemo response can also be potentiated by altitude. So this graph here, we have PaCO2 on the x-axis and methylation on the y-axis. And what this is showing is the chemo response before and after in 8-hour exposure to altitude. So that will be the AM and the PM. What it's showing is that the slope. So when we have an increase in PaCO2, we also have an increase in methylation. What this is showing is that over course of colonization to altitude, there should shift, and then there's also a steeper slope in that increased methylation. What we want to know is what happens when we add both of these together. So we know with exercise, the chemo response doesn't quite increase no matter what intensity. Even though we change the intensity, it doesn't increase. We're just saying if we increase the resting chemo response, what does that do to the chemo response during exercise? This leads to our research question we can ask saying, does altitude exposure further increase exercise-induced potentiation in purple hypertonic chemosensitivity? Going forward, I just refer that as PHC. So we hypothesize that the magnitude of increase in PHC from rest to exercise will be less in altitude compared to low altitude. So for methods, we recruited 21 participants, half of them female. And our resting values, there's greater heart rate and ventilation at high altitude compared to low altitude. During maximal exercise, they all reach similar ventilations, but at a much lower work capacity, work rate at high altitude. And at the respective gas exchange thresholds, they achieve similar heart rate and ventilations, but obviously at a lower work rate at high altitude. So how our protocol for determining PHC, we would do 5 stimulus at rest and 5 stimulus at exercise. So we have for each participant rest on a bike 5 to 6 minutes. We'll give them hyperkinetic stimulus, so this is about 10% CO2. Normally we breathe about 0.04% CO2. So one stimulus is 2 breaths of CO2. And then we'll give the stimulus 5 times for each stage. So we do this at rest, we also do this at exercise. And what we do to analyze this, we graph an average of all 5 stimulus, and that will be one representative response. So one at exercise, one at rest, in both low altitude and high altitude. So specifically, how do we quantify this response? On the top graph, we have floor inspired. So whenever the trace goes below negative, below 0, that indicates an inspiration. But just before it goes negative, that indicates is an end of a breath out, so end expiration. So what we're looking at on the second graph is end-tidal PCO2. So changes in PCO2 at a mouth. So what we see that increase in the middle, that is our true breaths of CO2. And because we want to line up in terms of when they are in a breath weakness cycle, we grab their steady state PCO2, end-tidal PCO2, and also the highest point after the true breaths of CO2. So it'll be this point here. We graph the difference between the two, and that'll be our change in end-tidal PCO2. We then also, that's the point that we grab. We then look at the inspired ventilation. So we have steady state ventilation pre-stimulus, and we look at the peak value post-stimulus. So that difference, change in inspired ventilation, when we grab the quotient of the two, so when we divide the delta PCO2 by delta VI, that gives us PHC. Okay. So what we've found, we gotta start with our low altitude results first. So panel A is individual responses, panel B is our average of all 21 participants. Open circles is resting, closed circles is exercise. And we see that exercise does increase PHC from rest at low altitude. With high altitude, PHC increases at rest, also at exercise. So even though they're more hypercapnic, or their starting PCO2 is much lower, the chemo response is much greater. So looking more specifically at the magnitude of potentiation by the two. So this panel first is looking at the increase in PHC by exercise only, and we're comparing between low altitude and high altitude. So at both altitudes, we see a 25% increase with exercise, and that's not influenced by whether they're in Bolivia or in Calgary. panel B is looking at the effect of altitude specifically, so we're comparing rest and exercise. So that'll be the increase in PhD by altitude alone. So when we go from rest to exercise, altitude leads to a 100% increase in PhD. So to conclude, altitude and exercise independently increase PhD. And mechanisms as to how they potentiate PhD are likely independent. And this is potentially due to the different sites of augmentation. Altitude will be more specific to the peripheral chemoreceptors. Exercise will be likely due to central command. And give them fun.
Okay, so I'll finish it off with, this is from my student Ben's work. So what we looked at this one was how high altitude affects the work of breathing. So when you breathe, this is accomplished through pressure changes in your thorax. So you expand your thorax up and that drives air into your lungs. And so to move your thorax, your respiratory muscles have to contract. Okay, so that contracting is what we quantify as your work of breathing. And so as you go to higher and higher altitude, so this graph here, we have altitude on our x-axis, barometric pressure on our y-axis. You can see that as altitude gets higher, the barometric pressure goes lower. So that pressure of air around you gets thinner. That's what we call thinner air up at altitude. So if we think of where we are in Calgary, again, I said about 1,100 meters. So you're kind of sitting just about there. Bolivia, about 3,500 meters is much higher than that. And if we want to go to the extreme, of course, Mount Everest, just a little bit lower than where, say, commercial airlines fly. You can see there's quite a lot less barometric pressure. Okay, so when you have less barometric pressure, the air becomes less dense. So if it's less dense, it's actually easier to breathe. Okay, so you can pull it in and out of your lungs a lot easier. And so when we think of that work that those respiratory muscles are doing, so we share it actually between your diaphragm, which is your main respiratory muscle, and that's the one at the bottom here. This is your diaphragm at the bottom there. So when your diaphragm contracts, it pushes down on your abdominal cavity, expands your ribs out. Okay, and then you also have accessory respiratory muscles. And these are the ones that largely expand out your chest. And we can quantify both of them by actually inserting an esophageal balloon catheter into people. So it goes up in through your nose, goes down, you can put one in your stomach, and that sits below your diaphragm. And then the other one sits in your esophagus. And then we get calculate the difference between the two, and that gives you your transdiaphragmatic pressure, and then all the pressure remaining that's associated with all the other respiratory muscles. Okay, so those are your accessory respiratory muscles. Okay, we can also split it into two different components of work. Okay, so when you take a breath in, the work is done to both expand the elasticity of your respiratory muscles. Okay, so your chest wall and your respiratory muscles, like most other biological tissue, has some elasticity to it, so you have to overcome that. And then you also have to overcome this resistive work. And so resistive work is airflow resistance. Okay, so just like any other fluid, there is some resistance to movement, same as blood, same as anything else. And so when you go to high altitude, it's typically this resistive component that changes because that is where we have a decrease in the air density. Okay, so we now think about it with exercise. So we want to quantify the change in the work that you're doing to breathe as you exercise. We have minute ventilation on the x-axis. So that'd be starting at very low resting intensities here. 200 liters per minute would be very high, very highly trained individual. The y-axis, we have again our work of breathing. So this is our quantification of how hard the respiratory muscles are working. And so we have this alinear relationship where as ventilation goes up, the work of breathing starts to go up exponentially. So you get these huge increases in the amount of work as your ventilation gets higher. And if we want to split this now into the different components. So on the bottom, this is another measure of work, but this is specific to the diaphragm. And on the top, this is all the other respiratory muscle work. And in general, they both are going to increase as you increase intensity. Okay, so both your diaphragm and the accessory respiratory muscles are both working harder. However, if we actually look at the ratio of the two of them, we see it generally actually falls with exercise. So while the diaphragm is working harder, it's actually doing a relatively lesser amount of that total work. So more of the work is being done by those accessory muscles. And so if you're ever watching, say, the VO2 max test or someone exercise, you can see this. So if you look at them low exercise intensities, you probably won't see any muscles in their neck or their chest wall very active. But at the end of exercise, you'll see the muscles in their neck, they'll start to become very active. And that's what's kind of indicating here, all those other muscles are really having to contribute a lot to the work. Okay, so what we wanted to quantify though was how does the diaphragmatic contribution to total work change at high altitude when the individual's exercising? Okay, so we questioned, does high altitude reduce the diaphragmatic work during exercise? And we hypothesized that diaphragmatic contribution decreased as we went up at high altitude. Okay, so very similar to the other studies, we had our cohort of participants, about half female, so they got instrumented with this dual balloon catheter. So again, it goes through the nose. One of the balloons, which measures the pressure, sits in your stomach. The other one sits in your esophagus above your diaphragm. And they did maximal exercise tests, the same ones that we talked about previously here, one in low altitude, one in high altitude. And so we have now an incremental increase so we can quantify the work throughout progressive exercise. Okay, so how we actually quantify work is, so here's an esophageal pressure trace. So this is that catheter that sits in your esophagus. And so when you take a breath in, your thorax expands and you get more negative pressure. So every time you see this value go down, that's a breath in, and going up is a breath out, breath in, breath out. So one way we can quantify this is we simply just integrate the area under the curve. Okay, so we just basically integrate how much work there is. And so as you can imagine, if you say made this much higher intense exercise, this value just gets bigger, which is generating more pressure. So for all the biomechanics, this is kind of our equivalent of quantifying work in terms of force over distance. Okay, it's doing a very similar thing. And we can also quantify it by looking at the relationship over volume. Okay, so this is now, we look at the, not just the force, but actually how it's changing over the changes in lung volumes. Okay, so this gives us what we call a pressure volume. This one down here. So we have volume on our y-axis, pressure on our x-axis. And so what happens is we start at this point E, person takes a breath in, so we can see the pressure gets more negative. And if you look at the volume gets bigger. Okay, so they're breathing in, the volume's going into their lungs. Now they get to point B, now they start breathing out. You can see the volume is going down. And so their volume is leaving their lungs and the pressure comes back down. Okay, and similar to the top one, we can integrate this area. And we can do a little bit of other fancy math that I can explain later if people want. But you can now split it into different quadrants, and that's how we quantify both the elastic work and the resistant work. Okay, so what we saw, so on the x-axis here we have ventilation, y-axis we have the pressure time product with quantification of total work. As expected, we see this nice increase in work with an increase in ventilation over time. Okay, so this is not overly surprising here. Similarly, the diaphragmatic work is increasing over time, a fair bit of spread here because it's the normal variability of individuals. And similarly, what we saw or what we see at sea level or in normal low altitude is the diaphragmatic contribution does decrease as your ventilation increases. Okay, so as you are working harder, your diaphragm is doing a relatively lesser amount of the work. Okay, so we also need to always make sure your kind of background is working. So when we went and looked at the components of the work of breathing, we found that it was the resistive work. So that's what's overcoming airflow resistance. That is what was lower at high altitude, and there was no differences in the elastic work. Again, this should make sense. High altitudes have really no effect of the actual inherent elasticity of your lungs and chest wall. All it's doing is impacting the air that's coming into your lungs. It was interesting though, is the work wasn't actually lower. Even though the ventilations were roughly the same. This is probably just again due to our participants were relatively trained, but as you get higher and higher in your fitness, your ventilation goes up, you get higher along that curvilinear response. So we were probably just on the edge of the touch underpowered here. Okay, so now if we split it into our again esophageal and diaphragmatic contributions. And we saw that there was no real difference at the same work of breathing, or at the same ventilations here until you got to these very high levels. And then when you got to these higher levels, you see this fairly substantial decrease in the amount of work that the diaphragm is doing. And so your total respiratory muscle works the same, but your diaphragm is doing a lesser and lesser share of this as the ventilation goes up. Okay, so this ratio would drop down to approximately 50%. So in other words, at max exercise in Bolivia, your diaphragm is doing about half the work versus it's doing closer to 2/3 of the work at Calgary or closer to sea level. Okay, so our conclusion is that the diaphragmatic work was reduced with no difference in total respiratory work, but this ratio changed as you got to higher altitude work rates, and it was the resistant work that was causing a lot of these differences. Okay, so with that, I will end, and then I think we'll take questions for all three of them together.
Who'd like to start us off with questions? Brian?
I can start. I have a question for, so when would you, so you have the incremental exercise, which is kind of like your ground truth VO2 max assessment, and then you had this, what did you call it?
The super max.
Super max test. When, why would you want to do that? Like, you kind of have, I could see like it's faster, it's quicker to assess than doing an incremental exercise. But in my mind, like, you still have to do the VO2 max incremental assessment in order to figure out what that 105% is, for them to do the super maximum exercise. But what's the, I guess I should say, what is the benefit of doing that kind of test?
So the super maximal test would just be beneficial if your main outcome that you're looking at is somebody's VO2 max, like if somebody did a training study, and so you want to see that they are, like, their fitness is increasing, so you want to see if their like VO2 max is going up, then if that's like your primary outcome, it would be beneficial for you to say that for sure that was their VO2 max. So if somebody came in and did a max test at the end of their training study, and then you do that like super maximal test, if those values are different, then you can say that like they didn't achieve their true max. So it's it's a good tool if like that's what your primary outcome is. And so then, because you don't always have that secondary criteria, like you don't measure blood lactate or the other stuff is like less well defined.
Okay, good. And then who figured out that it was 105 was the magic?
There's a few different studies that have done a few like different ones, like 105, 110. Our lab had previously done 105%. So for like consistency, we did the same one in Bolivia. Then that was our like hypobaric hypoxia versus our normal baric hypoxia.
Where does that, how do you get funding to do this? I mean, I know Trevor's got the NSERC and probably some of his NSERC goes towards this trip, but I assume that an NSERC discovery grant for one person can't pay for how many people went, 30 people or something like that?
Maybe I'll answer that. So I can't speak to some of the other international people. So Trevor and Richard got one of the transdisciplinary connector grants, I believe. And so that paid, I'm going back to our people, that paid for the use of the High Altitude Institute. So they pretty well put it to that. Each individual kind of group was responsible for their own students. So pretty well anybody from, us, UBC Western, and then Trevor and Richard was all basically done out of our NSERCs. Then I'm not sure, I believe the Irish group got a specific grant for their one. The people from Loma Linda didn't have a lot of expenses other than kind of their travel expenses. They did a bunch of wearable things, so it's a fairly kind of low expense one. I'm not sure the French group, they had a full polysomnograph, so that takes a fair bit of cash to do it, but they would have already had that ahead of time, so. Other than the travel, there wasn't a huge amount of expense associated with it.
Do I see other hands? Go ahead.
I'll ask one for anyone but Pablo. Not specific, I'm interested in, like, how much altitude is enough? I've got two questions. So what's the, like, altitude elevation where you start to see real, like, true physiological differences change in performance? Like, what altitude, like, is Calgary high enough for that? I don't know. What's that kind of?
Yeah, you can see some changes starting in Calgary.
The lowest is at 5 feet. There you go.
Say that again?
The lowest is 580 meters, where they see a reduction in performance.
Okay.
Yeah, or half calorie altitude.
So then my follow-up is for training, or, like athlete training, what this, some athlete can do, I don't know, diners athletes, like, I really think that a higher altitude would benefit me. What would you advise them? So if we're already at somewhere where they're seeing a physiological benefit, but is there any point in doing something different?
Did you repeat the question?
Diners athlete comes to you and says, I was saying endurance sport, comes to you and says, want to get benefit from training at altitude. I'm training harder right now. What would you advise them to do?
I think that usually like, if you're traveling to an altitude, if you have to travel to an altitude to train at, then it's expensive. And depending on where you're going, like, you can't drink the water in Bolivia, so a lot of people were really sick on our trip. So you're going to train there, like, unless you're there for a long period of time, you're maybe not gonna see the benefits, so. I don't know, it's maybe not super beneficial, depending on where you can go to.
Yeah.
If you're already in Calgary, maybe you're already getting the best benefit.
Thanks.
I guess follow-up question to that is the answer like the higher the better? If you were, say, training in a hyperbaric chamber and you wanted to train at like should I just set the altitude to Everest? Am I getting like awesome benefits from that more so than if I?
You're not awake if you set the altitude.
Okay, well, that's a little bit lower than that. Let's say if I set it to, I don't know, 8,000 meters, or sorry, 6,000
Still
meters.
dead.
8,000 is pretty hard, yeah. But you get the essence of my question is, there obviously is a limit to the benefits, right? If I'm dead at 8,000 meters, not exactly beneficial.
I don't know if there's a.
Does it depend on the person and how fit you are currently?
Well, some of it's gonna depend on like how much exercise you're able to perform. But where's it start? I don't know what this is like, that altitude is. Victoria, okay.
I think the thing that you have to keep in mind is that performance, like your VO2 max, like wherever that absolute workload is, will 100% decrease the higher up you go. So that kind of means that you're working so much harder at a higher altitude, but you're not exactly performing the same amount of external work. So that's why they kind of suggest in terms of, live high, train low. That's because you do train a lot harder at lower, like at sea level than you were if you're at higher altitude.
So you can effectively practice your high output training, but then get the physiological benefits of living at high altitude. That's what the live high, train low means.
Where is that now? I remember that being a huge thing, like 20 years ago, live high, train low. Where's the state of exercise physiology right now? Are we still saying that?
It's you ask.
Well, I'm asking you. Or your group.
Yeah, so maybe to wrap up, so yeah, the higher you go, like, you just can't do it, right? Like, above 5,500 meters, you're not able to do a whole lot at all, so you just can't train up there. Even say at Bolivia, 3,000 meters, you just can't work nearly as hard, so you don't get that kind of training stimulus that you would. You can try as much as you want, you're just not getting any peripheral adaptation, so you're actually detraining as you go up there. So there's no benefit of living very high and training very high. Sure, you'll produce more red blood cells, but you're literally detraining. So then the live high, train low is like, where's the sweet spot of sleeping high enough, living high enough that you can get those potential positive adaptations, but training low enough where you can still train as hard as you need to sea level, right? Like, in a perfect world, the person basically flies down in a helicopter a couple times a day, trains at sea level, and then flies up and rips at say 2,500 meters or so. He does that. Now, why I say it depends on who you ask is there's a bit of pushback among some people in that. Is it really actually a performance benefit, or is it just because people are living and training together? Because typically you do it in a group of, 20 athletes or something, right? So it's like, well, if you're just taking them and they're living and doing this camp and they're living at high altitude, all they're doing is training. That's probably pretty good for them to do that. You do certainly see some increases in, say, hemoglobin or other things, but those don't always translate into performance outcomes. The biggest pushback study was they had a hypoxic house where they have individual rooms, different levels. So all the same subjects, they're all living in the same house, all doing the same training. Half of them slept at low altitude, half of them slept at high altitude. They showed no difference in performance. The whole wild card in all of this is it's all dependent on hemoglobin. Don't have enough iron, will make hemoglobin. Athletes are notoriously low in iron typically. So you can't just send them to high altitude and think they're better. You have to make sure they are going to get that benefit out of it. Then some people react differently to high altitude. So like if the comment going higher, you go much higher than 3,500 meters, nobody sleeps. You just don't sleep at all. That's very poor sleep quality. So that's definitely got a huge impact in your training if you're basically awake every half an hour because you're gasping for it. So it's really kind of finding that sweet spot amongst all those things.
Do we have an online question?
Yes, we have an online question. So as the energetic cost of breathing increases such as high altitude exposure, what adaptations does the diaphragm undergo to meet the metabolic demands? Does it adapt similar to other muscle?
Great question. I'll answer that in summer 2027. We don't know. There's been very little work in the adaptation. Like we know the work gets harder. I should do this the first interview. The work gets harder. We have no real idea how the diaphragm adapts. For example, what is the hypertrophy? Is there a fiber type shift? Does it improve its blood flow? We don't know any of those things. So it certainly gets placed on a higher demand. We don't know how it accomplishes that. The other thing we don't know is if you're now at high altitude for a week doing intense exercise, we know your diaphragm can fatigue under certain circumstances at sea level, presumably would fatigue more and greater at high altitude, because now that energetic demand is just constantly elevated. Again, we don't actually know what that does. Give me a few years and I'll give you an answer.
27.
I had a question kind of going back to the different ones that were asked. So from Leah's study, we found most of the metrics that you were measuring were pretty similar at low and high altitude. And then Victoria's study had a few differences in the chemosensitivity. And then the most drastic differences I saw in the last study were with the work rate being done. So if we were to tie all of that together, are we saying then that there are huge differences between low altitude and high altitude? And like, how does that affect an athlete's perception of like going? So for example, Neymar that you gave as an example in the beginning, what would you tell him? Like, is it now all of a sudden okay to go and play their matches in Bolivia, or did your results point the other way?
Yeah, was your trip funded by the Brazilian soccer nation?
Not. It depends on what you define as it's okay, right? So I mean, why FIFA did that? They didn't want they basically wanted the quality of the game to be as high as it could be. The quality of the game is low. Like there's no way around it. You go to 3,500 meters, you can't run as fast. You can't do anything as well. Your VO2 max is substantially lower. So they said like that's nothing to do. So it's really the question of what does it matter? Where people think it's unfair is they would say, well, the Bolivians are living there, which is not necessarily true because if you're on the team, you're probably playing internationally, right? But we'll just assume they all live there. Okay, well, maybe they have some adaptations from living there, or they acclimatize to it. That if you're the Brazilian team, you just fly in there for the day, and then you're going to get hit way harder, right? You acclimatize over the span of multiple weeks. So that's where they kind of feel it's unfair. I would argue that's no different than talking to people the other day when last World Cup qualifier, Canada played Mexico in Edmonton in winter. You have cold acclimatization, then the opposite happens. If you have a bunch of European or Canadian athletes who are playing the season in the fall, and then you bring them down into Central South America, they are not acclimated to the heat. So they are at a huge disadvantage compared to that. So I don't know the inner workings of FIFA. That's my guess of why FIFA ended up kind of revoking it, or they kind of got rid of it, because altitude affects everybody. Even if you're fully acclimatized, you're still never back to sea level. So it's not like some magic cure. Everybody's kind of worse off. Is it really fair to say punish the Bolivians, who that's where their stadium is, to say they can't play there when this happens all over the world, right? Hot, cold, pollution, lots of other things. So is there an okay? No, there's no okay at altitude. Really, how much do you want your performance to decline? It's really what it amounts to. And you see that Olympics in Mexico City. There were no records for any distance events, because you're at 2,500 meters. But you don't get good records for throwing events because they're explosive and the air density is a little less. They're to throw things farther.
Yeah, the question, Jen. My question's for Victoria. So I was just curious why you did your measures up to GT. I'm assuming that you guys wanted to avoid like the buffering and things that happen after GT, but just curious, like, why is that important?
Well, the short answer is that the intensity actually doesn't matter.
Okay.
And then because there is also a previous study where we kind of look at THC super like above threshold, and we're comparing like the resting the resting response before the exercise and also after exercise, because like, and we test this like right after, and we expect it to be so like right after exercise you're still hyperventilating, and then you're blowing out all that CO2. We expect the chemo response to be different. We don't see a difference. So like it's not due to the things that occur with exercise, like, you know, increase in catecholamines or like metabolic levels. I think we just like picked threshold acid intensity, but there's no like and also we're how like our study is like intermingled with other studies as well. We have another student from UBCO, like she needs a specific intensity because she was looking at a pico. So like which that is like for exercise, blood flow occlusion. And so she needs a specific intensity. So essentially we just like adapted our protocol to what others are doing. Because essentially it's like under the same protocol, we grab different data. That's essentially how it came out to be.
Okay, so then if you're testing like maybe RCP, like in the heavy domain or above that, do you think we'd see a difference in hypercapnic sensitivity?
No. Because I think recently someone did everyone do that? Yeah. We did assess for VHC at those higher domains. Yeah.
Any other questions for, Adam?
Leah, you mentioned that there's kind of like two ways to be hypoxic. Right, there's like partial pressure and there's concentration. Is that, what's the definition of that again?
Like the fraction, so normal baric hypoxia, so if we're sitting here, if I was to make you hypoxic, I would give you a lower percentage of oxygen to breathe, like we breathe 20.93%, so I'd give you like 15%. Whereas like when we're in Bolivia, you're at hypobaric hypoxia, so the 20.93% of oxygen is still the same percentage in the air, but we're at a higher altitude, so the partial pressure is lower.
Okay, so then to clarify, the studies that Paolo presented were normobaric at Calgary altitude.
Yeah.
Which was just as you described there versus hypobaric at Bolivian altitude.
Yeah.
Okay, so then Paolo mentioned at some point that at high altitude, the thin air means that the diaphragm doesn't have to work as hard to bring air in. Is that a correct statement?
All respiratory muscles, which is
All
what you
respiratory.
the air is thinner, so it's less turbulent, so it's easier to breathe at high ventilations.
So is then one of those ways, like, one of those types of training, say being in a hyperbaric chamber versus breathing normobaric oxygen, lower concentration oxygen, is one of those like a better way to train your respiratory muscles?
So these differences at most training intensities are fairly minimal. So air density certainly impacts the work, but you have to get either very high altitude or very high ventilations, because basically airflow can either be laminar, transition with turbulent. Turbulence, when you see a river, it's kind of churning, that's very inefficient. Laminar, everything's going straight. Low ventilation, therefore, is laminar, and that's why we see the work is fairly low, like it's that kind of low slope of the work of breathing, right here. And then that kind of kick up right here, where it really starts to go up, that's when airflow transitions to more turbulence. So I can kind of see where you're getting at, okay, if you're at low altitude, normobaric hypoxia, the air is thicker, are you working on your respiratory muscles more? In theory, yes. At these low ventilations, though, your respiratory muscles are doing such a small relative amount of work compared to what they could do at max. So they're not really getting any kind of training stimulus there. It's just too small to really have any differences. Maybe if you were kind of all the way up here, but you're not typically training for prolonged periods at your max ventilation. And it's just not sustainable enough. And then that ignores the aspect that your respiratory muscles are typically not what's actually limiting your exercise performance at sea level anyways. Maybe at higher altitude, but at sea level, they're not what's stopping you from exercising.
Okay, I haven't seen any more hands go up, so if there are no more questions, let's thank the speakers.